In the final video for this lesson, we'll consider what happens when I try to multiply two power series together. What sort of thing do I get? What would that look like? And then we'll use that to solve, to try to approach and solve a problem. If you have, say you have two power series that have the form, how about a x to the n, and I want to multiply this power series, how about n goes from 1 to infinity, with a different one. How about call it this in the coefficients b's? I'm multiplying those two things together. What will I get? Well, this is this first thing is just a polynomial that starts at a0, a1 x to the 1, a2 x squared, a3 x cubed, and you keep going. Then multiply that by the same thing just with b's. How do you multiply polynomials? Well, you FOIL or box multiply or whatever your method is for distributing and combining terms. In the end, you're going to end up getting, well, a polynomial times another polynomial is still a polynomial. So you're going to get another power series. So the theorem says that the product of two power series is itself a power series. We'll call it the coefficients. Well, C is the next letter in the alphabet. Where the coefficients have the following form. Well, how do we calculate this? Well, we can multiply these two polynomials together and try to figure out what are the constant terms, what are the first power terms, what are the second order terms, and so on. One way to multiply is to multiply using a grid. So I'm going to make a grid out of this. I'm going to write this first polynomial going across the top. a0, have a1x, a2x squared, a3x cubed. And you keep going. And then I'll write the second polynomial going down. So this is b0, b1x, b2x squared, b3x cubed, and you keep going down. And the product of these two things is what I get when I multiply by down and across. For you biology people, this is like making an infinitely large Punnett square, if you will. So the product of the constant terms is just a0, b0. The term that comes down below here will be a0 times b1x, or a0 b1x. Over here should be a b0 a1x. In this space, I'll have a b1x times an a1x, which is an a1 b1 times x, which is x squared. And I keep filling in this table. How about, I'll do a few more. How about a0 b2 x squared times a constant is x squared. How about a2 b0 times x squared. How about b2 times a1 x squared times 1x is x cubed. b1 times a2 x times x squared is x cubed. b2 times a2 x squared times x squared is x to the fourth. And I'll fill in just a few more. a0 times b to the third, a0 b to the b3, excuse me, x cubed. How about a3 b0 x, nothing times x to the third is x to the third. And you could continue filling in this table. What are these c's? Well, c0 is the coefficient in front of the, a constant term. What's the constant term? Well, it's just here. This is c0. what is the coefficient in front of the x to the first powers? Well, it's the sum of everything that has an x to the first power in it, and it looks like it's these terms. If I factor out the x to the first term, that's an a naught b1 and an a1 b naught. What's the second coefficient, or the coefficient of x squared in my product? Well, it's the sum of all the coefficients of x squareds here, and it looks like it's these guys on this diagonal here, which is a naught b2 plus a1 b1 plus a2 b naught. And again, you could find the cubic term. And maybe something that I noticed, so I don't need to keep filling these in, are that the subscript of c is just all of the combinations of a times b, so that the subscripts add up to the subscript of c. So this is like a naught b3, a1 b2, a2 b1, and a3 b naught. And if you keep going, this is how you calculate values of c. Here's an example of a product of two power series coming in useful to solve a problem. So here's this expression, and so the sum from n equals 0 to infinity of this power series a sub n x to the n. We're going to say this is the expansion of x divided by sine x. For some x's, as long as x is not a multiple of pi. Otherwise, we'll divide by 0. So we're going to use the Maclaurin Series expansion of sine x, which is known and was in one of the homework sets, and I'll state it when we need it, to figure out what looks like a second degree estimation of x over sine x is. So note we're saying that according to our assumption, that this sum n equals 0 to infinity of a n x to the n is equal to x over sine of x. Or maybe if I do a little rearranging, this says that whatever the sine of x is times this infinite series this is equal to just simply x. Or, better yet, so this says that if I did a naught plus a1x plus a2x squared plus a3x cubed, and I kept going, I multiply that with the expansion of sine. You can look this up in the book, or if you recall from one of the previous homework sets, that the expansion of sine of x, or the writing sine of x as a power series, is the following form. It is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and alternating, so on and so forth. What is this product equal to? It's equal to just x. Since these two things are equal, that means that term by term they have to be equal. Meaning that whatever I get when I'm done multiplying this polynomial out, it's got to be equal to x. So that means all the x squared terms, the coefficient in front of the x squared terms is 0. Coefficient in front of the x to the 5th terms is 0. Coefficient in front of the x to the 100th terms is 0. The constant term is 0. And the coefficient in front of x is 1. So I'm going to figure out what are the since I want to estimate sine x as to the x squared term, I'm going to figure out what are the values of each of these terms each of these things in terms of x in front of each of these x's. I know that if I wanted to, I could write x as 0 plus 1x plus 0x squared plus 0 x to the third, and so on. If I multiply this out, what do I get? I get, let's see, what's the smallest power of x that I'll get? I think that's what I get when I get a naught distribute to this x. Can I get an x? I can't get a constant term because every one of these has an x in it, so when I distribute I'll get an x, so there's no constant term. Let's see, what would the x squared term be? How can I get an x squared term? I only have odd powers of x over here, so to get an x squared term I need to take even powers of x over here and multiply. So I think I could distribute this a1x to this x here and get an x squared term, and that's it. Because there is no x squared term to distribute the a naught to, and there is no constant term to distribute the x squared term to. So to get an x squared term, I need to take this a1x and multiply it to this x. To get an x cubed term, let's see, how could I do that? I could take the a naught and multiply it to this term that's got an x cubed in it. Are there any other ways I could get an x cubed term? I can't multiply this x to anything over here. That'll give me an even power. I could multiply this a2 times x squared to the x. I get a2x cubed. I can't multiply the a to the this a cubed with anything over here because there's no constant term, so I'm going to get a bigger power x. And I keep going. So what does this tell me? Well, I think this exactly tells me how to calculate a naught, a1, and a2, just like I need in my answer. I know in order a naught is the term in front of x. The term in front of x in my answer is 1. So this tells me that a naught is 1. The x squared coefficients need to match up. The x squared coefficient on the right-hand side is a1. The coefficient of x squared in the left-hand side is 0, so a1 is 0. The coefficients of x cubes need to match up. The coefficient of x cubed on the right-hand side is minus a naught plus a2. Factorial. Minus a naught over 3 factorial and a2. And those have to add up to the coefficient of x cubed on the left-hand side, which is 0. And we know that a naught is 1. So minus 1 over 3 factorial, which is 6, plus a2 is 0. a2 is 1/6. So x over sine x is approximately to the third degree a naught, which is 1, plus a1 times x plus a2 times x squared, which is 1 plus 1/6 x squared.